Discord. And that should be on. Let's see. Yeah, and we're off to the races. Okay. Okay. So if you still needed more practice with fractions, we're moving on from fractions to a topic on order of operations today. And some of you guys might be familiar with order of operations, but if you still needed help with fractions, you got to get into the homework and practice as soon as possible, so that you can run into those speed bumps. You know, if you hit a brick wall, that's where, you know, you need to reach out for help immediately, get that practice, make those mistakes, and then figure out, you know, what mistakes you're making and correct them. But on this topic of order of operations today, we're going to talk about algebraic expressions that combine more numbers with more mathematical operations. So when I say arithmetic operator, I mean like addition, subtraction, multiplication, division, and then we have more operations that we're going to learn about throughout the course of the semester that we're going to have to become familiar with. So let's start this thing off with giving a definition of an algebraic expression. Okay, so what is an algebraic expression? An expression in mathematics is just a statement. You can think of it like a sentence. Like if I had an apple and 2 bananas, I could write that out in plain English, 1 apple, 2 bananas. Or I can use a variable to say let A be apples and let B be bananas. And I can put 1A plus 2B. And symbolically, that would be my representation or my statement that I have 1 apple plus 2 bananas. But an algebraic statement combines numbers, variables, and arithmetic operators or operations. Okay, they can be manipulated and they can be simplified. As an example, I said, let 2A, well, let's say I had 2 apples in this case, plus 3 bananas. Here, the variable or the variables are the letters, right? Where A is going to be representing a physical quantity, apples. And B is going to represent some other physical quantity that's not the same as apples, right? Bananas. So here, our variable is just a placeholder for some object, okay? And so I can write this statement down that I have 2 apples plus 3 bananas. So in mathematics, that's the only reason why we use letters. They're placeholders for some object, right? And so we can talk about things in the abstract and we don't have to talk about the actual physical things. It's sort of like a code. Okay, but that being said, this expression here, 2A plus 3B, has the arithmetic operation of addition, but there's some other stuff going on that we have to talk about. So some words that you might hear me say are terms. And in an algebraic expression, terms are separated by either addition or subtraction. So can anybody tell me how many terms are in this expression here?
Just one term?
Well,
2.
the addition symbol is separating our terms here.
Right.
Like we're talking about 2 different kinds of objects. So we're talking about 2 terms in this expression.
Okay.
This is one term, and then this is the other term. So if you have one operation in the middle of them, then really they're separating 2 terms. Okay. And you might think that that's a little bit, I don't know, maybe a little bit esoteric or a little bit very precise or nitpicky, but it's going to be very important for you to be able to look at a string of terms and count how many terms there are. Because as we get to the topic of polynomials later in the semester, you might have a 3-term problem that we have to process in a different way than we process a 4-term problem. So being able to recognize how many terms is very important. Okay. The other thing here is that we have variables. That's going to be a placeholder for an unknown value. So a variable is just a placeholder, a symbol, usually a letter, but it represents an unknown value. What do I mean by that? Another way of putting it is that if I go to one supermarket, apples might be, let's say they might be 98 cents for an apple. So what I could do to find out the cost of just the apples, if I'm focusing on just this part of the expression, is I could take that 2, if I have 2 apples, and multiply it by the cost of the apples. So the cost of the apple here would be 98 cents. So 2 times 98, right? But if I went to a different supermarket and maybe they had bigger or slightly different apples that were, you know, $1.25 per apple, then the value of A will change, right? So it's going to be context dependent what the value of the variables are. Okay, and usually when we're what's called evaluating an algebraic expression, which we'll do a little bit later, I will give you a value for the variable. You're going to plug it in, and then you're going to multiply some stuff out and simplify your expression. Okay. But in my explanation there, I sort of already said that there is an implied operation between this 2 and this variable A, and that implied operation is multiplication. So we call the 2, or the number in front of the variable, the coefficient. So some more vocabulary coming your way. That's the number multiplied by the variable. And you're not going to see a time symbol. You're not going to see the X because our variables are letters. So one of our favorite variables to use in mathematics is X. And that gets a little bit confusing when you have X for the multiplication symbol and X for a variable, because you don't know which symbol is which if you're writing very quickly. So a lot of times what you'll see me do is write a dot as multiplication or use parentheses as multiplication. But when it comes to a number and a variable, we don't have to write anything between them. And if there's no operation between them, it's implied that it's multiplication. It's sort of like the default operation here. Okay. Constants or constant terms are known fixed values. So let me give you an example of an algebraic expression that has a constant in it. Clearly, these 2 terms are both variable terms because they have a letter incorporated in them. So those are unknown values that would be given to you at some point. But an example of algebraic expression that has a constant and variable terms would be like 3x plus 5. Okay. Again, this has 2 terms. The terms are separated by the addition symbol. This first term is a variable term. It has a coefficient of 3. And this term over here is a constant. It's not attached to a variable, so that value doesn't change. We know the value of that, and it's the number 5. So let's say that X here represents, I don't know, let's go with apples again. So if I wanted to buy 3 apples and at this store, for whatever reason, they have like, I'm going to use my credit card, and they have some sort of weird system where if I need to use my credit card to make a transaction, they're going to charge me $5 for that. I know it's not realistic, but let's just go with that example. Well, because I don't have any cash on me and I really want these 3 apples, I'm going to pay for the 3 apples. So that would be 3 times the cost of the apples plus this flat fixed fee of $5, right? So that's how we could sort of interpret this algebraic expression. It has a variable term, it has a constant term, it combines numbers and variables with our arithmetic operations, okay? Okay, so now we've been dealing purely with numerical operations when we were doing all those fraction problems. We were just strictly taking a number like 1/2 plus 1/3. We had to process fractions a lot so that we could actually do that addition or subtraction, especially if they didn't have common denominators. So we're going to need those tools in our toolbox. It's not something that we can forget. Everything in this course is going to build up. But now we're going to need to be able to manipulate these algebraic expressions that have more operations than just a single addition or a single subtraction. So let me introduce to you a new operation. Maybe it's not that new. Maybe some of you guys have heard of them and used them before, but can anybody tell me what an exponent is?
I guess it's how can I explain? It's a number that multiplies. I don't know the rest of the word. I don't know how to explain it.
Yeah, no, I think you're on the right track though, because you're talking about multiplication and that's where you need to be.
Right.
It's a number that's multiplied by the number at the top, right? But it's by
Right.
itself, multiplied by itself multiple times.
Yes,
Right.
that's exactly it, right? So like in grade school, when you learned about addition and subtraction, those were sort of the basic operations that we learned as kids. And then you go on to multiplication and they teach you that multiplication is repeated addition, right? Like 2 times 3 is the same thing as 2 plus 2 plus 2. You have 3 copies of 2 and you can add them repeatedly. And that's multiplying, right? So multiplication is repeated addition. Or at least that's one interpretation of it, where 2 times 3 is like saying that we have 3 copies of the number 2, 2 plus 2 plus 2, and we get 6, right? Alternatively, you could say that we have 2 copies of the number 3, 3 plus 3. Either way, you get 6, right? And so that's how we define multiplication. Well, exponents or exponentiation, if you want to sound fancy, is repeated multiplication. So if I had something like 2 to the 3rd power, and that's how we talk about them, we talk about them as being powers. This is 2 raised to the 3rd power. Then I could write that out as repeated multiplication, 2 times 2 times 2, which would be 2 times 2 is 4, 4 times 2 is 8. Okay, so the notation for exponential expressions is this. We could have a raised to the n is equal to a times a times a times dot 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 times a. So imagine that we let a represent a number, some number. And we're going to let n represent usually some whole number. Or at least for our purposes right now, we're going to use whole numbers. Okay. So what this expression a to the nth power is telling us to do is to take this number at the bottom, and we call it the base of the exponent. We call this the power, or simply the exponent. We're going to take that base and multiply it by itself n copies, right? N number of times. So for, as in this example, 2 to the third power means we're going to take the base 2 and write 3 copies of it, and then run through that multiplication. And the way we talk about this is we have a raised to the nth power, or we just simply say, this is sort of a casual way of speaking, a raised to the, and I might not even say raised to the, I might say a to the nth. Sort of like math slang. So let me give you guys a moment to write that down if you're taking notes. But does anybody have any questions about that? Okay. Well, let's look at some examples. And I'm going to make the examples primarily be fractions so that we can get some practice doing some fraction multiplication. Let's start off with, actually, let's start off with a whole number. Let's do 4 to the third power. The instructions for something like this might be simplify the exponential expression, or just simplify the expression. And when we're saying simplify in mathematics, we mean a lot of things by that. But for these kinds of problems in this context, if you're simplifying an exponential expression, it means just quote unquote solve. Or you know, 4 to the third power, we can actually run through that multiplication. So what would you get if you simplified this exponential expression?
64.
Yeah.
I don't know.
Does anybody get something other than 64? Or is anybody confused as to why it should be 64? Okay. Well, the reason why it's 64 is because we're going to apply that definition of our exponent. This is repeated multiplication. So I'm going to have 3 copies of 4. I'm going to multiply those together. And when we multiply numbers, we just do it 2 at a time. So this will be 16, 4 times 4. And then we need to multiply that by 4. And so you could do that by hand. If you wanted to do some scratch work off to the side, you could do 16 times 4. And then 4 times 6 is 24, so that you would have 4 down. 4 times 1 is 4, plus 2 is 6. So, but that's also why calculators exist, and you could have just thrown that into the calculator. Right? 64 is the simplified form of 4 to the third power. Right? Those are the same value. You could write it as 4 to the third power, or you could write it simply as 64. Okay. Let's look at another example. Let's do 1/3 raised to the second power. What does this simplify to? Get you some fraction multiplication practice.
Is it the same as 1/3 times 1/3?
Yeah, that's the definition of exponentiation. If you have 1/3 raised to the second power, then by definition, you're going to write 2 copies of 1/3 and just multiply that out.
So would it be wait, hold on. 1/9?
Yeah, because when we're multiplying fractions, we just multiply straight across. So 1 times 1, multiply those numerators, you get 1 as our new numerator. And then 3 times 3 is 9 on the bottom. So 1/3 times itself is 1/9. Anybody have questions about that?
The parentheses is just like to put the whole fraction in there, like.
Yeah, so in mathematics, the parentheses is just to be a little bit less, you don't want to be ambiguous with the symbols that you use. And so as a note, if I wrote 1/3 and I just put the 2 right here, it looks confusing because I don't know if it's just the 1 that's raised to the second power or if it's the entire fraction, right? So if I saw something like this, I would think that this is 1 times 1/3, which is just 1/3 still. So we enclose the entire fraction in parentheses so that you know the exponent is applied to the entire fraction, both the numerator and denominator. So whatever's in the parentheses, that's what gets copied however many times, right? In this case, it was 2 copies of 1/3. Does that make
Oh,
sense?
okay, I see. Yeah, that makes sense.
Yeah. Okay, good question. Let's look at one half raised to the 5th power. I'm gonna give you guys a couple minutes to figure that one out. And then maybe 4/7 to the 3rd power.
You slide the paper down. I don't see the,
Oh, my bad. There you
So-
go.
thank you, sir.
You got it. So we have 1/2 to the 5th power, 4/7 to the 3rd power. And then you can just throw a thumbs up in the chat or use the reaction to throw a thumbs up to let me know that you're done with one or the other. Sees we have a few people that have completed both of them, I think, but what did we get for the first one?
I got
1/32? Is that correct? Or did I?
Is it 32? Let me see. 2, 4, 8,
I got the same answer.
16, 32. Yeah, that's right. So we could go ahead and write this out as 5 copies of 1/2. And we're multiplying those together. 1, 2, 3, 4, 5. And 1 times 1 times 1 times 1 times 1, it's just going to be 1. And then you'll find out that 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And then another 2 makes that 32. Right? Okay. What about this one here? Let's see, we have 4/7 times 4/7 times 4/7. So I know the numerator is 64. What do we get for the denominator?
I got 343.
343. Yeah. Yeah, neither of those fractions simplify any further. You might ask me, how do I know that? Well, if we look at the first fraction, 1 doesn't simplify any further. It doesn't have any common factors with 32. So that one's done. This one, you might look at 64 over 343 and think those are pretty big numbers. They have to reduce somehow. But that's not true. They have to have common factors in order to simplify. And since 4 only has common factors of 2, I have 2 times 2, 2 times 2, and 2 times 2. 7 is a prime number. So these 7s on the bottom won't cancel out with any of the 2s on the top of this fraction. Does that make sense?
Mhm.
So since I know that the numerator here has no prime factors in common with this denominator, then it's not going to be able to simplify any further. It's fully simplified. Okay. All right. Well, now that we've done some problems with exponentiation, we can start talking about combining our algebraic expressions, sort of expanding them so that we have more operations. So order of operations. This phrase is used in mathematics to just really describe the consistent steps that we need to use to simplify a complicated algebraic expression so that anyone who works to simplify that expression will come to the same result. Okay, so it's a way that we need to make consistent, make the process of simplifying algebraic expressions consistent among all people. So let's think about this for a moment. Maybe I'm going to use this as an example. Let's say that we had the expression 11 times 6 plus 10 times 19. Okay, I want you to work this problem out, simplify it, and then we'll discuss what we get. I'm not going to tell you what order in which you need to do the operations. I'm just going to say, take a crack at it, see if you can get a simplified result, and then we'll see if we get different answers. And then when you get a solution, or when you simplify this expression, you can go ahead and throw that in the chat, whatever that number you come up with. It seems like we're getting pretty consistent solution here. Did anybody get something different than 256? Okay. Did anybody get let's see. $1,444. So somebody's getting 12,540. 513. And somebody got 1,444. Okay. Let's see. Okay, let's do this. It looks like the majority of people are saying that this should be 256. But some people are saying that it should be 1,444. And then some people are saying 513. And then we have another one that says 12,540. 12,000.
No, sir, don't write that number. I multiplied instead of adding. That was the
Oh,
wrong
okay.
one.
You multiplied
Yeah.
all of them out. Gotcha.
No, yeah, just don't ignore that.
No, that's fine. But let's talk about some of these, right? So like, it seems like the consensus among the class is that this should be 256. But if you were to just run through this problem left to right, doing the multiplication, then the addition, then the multiplication, you would get 1,444. I'm not sure exactly how the 513 came about, but in any case, clearly we can get different results if we use different ordering of our operation. So let's take a look at that problem one more time and sort of discuss it at length. So let's say that for whatever reason, we lived in a society and a culture where in mathematics, we did the math, we did the operations in the order in which we read. We read from left to right. So if we just did left to right ordering, we would have 11 times 6 plus 10 times 19. This would be 66 plus 10 times 19. Then this would be 76 times 19. And then you could do this by hand here, or we could just, throw this in our calculator, 76 times 19, and we get this number here. But if you do some other ordering, where you say, okay, let's look at that same problem. But this time we're going to say that we're going to take care of all our complicated operations first. And so for some reason in our head, we think that multiplication is a more complex operation than addition. So I would take care of my multiplication first here, get 66. Then I would jump to the back of the problem and say that this is 190. And then I would just add those two together. Well, that would give me my 256. And so which one of these is right?
256,
Yeah, and why is it right?
because we're following the operation of PEMDAS.
Yeah. So you guys might have heard about PEMDAS in a previous math class, or every now and then social media will blow up with people arguing about some math problem that needs to be worked out using the correct order of operations, and people in the comment section will be like angrily yelling at each other about, the answer should be this, no, the answer should be that. And it turns out that the order that we do our operations in, again, like I said, is just to be consistent among us. And so mathematicians decided that we're not going to do the math from left to right. We're going to use some other ordering. You may have heard PEMDAS. I like to say we're going to use GEMDAS, because I think that PEMDAS leaves a little bit out of the story. Okay, so in PEMDAS, this acronym, the P stands for parentheses, that if you have an algebraic expression, that you're going to complete all of the tasks inside of a set of parentheses first. But parentheses are not the only type of grouping symbol. So that's why I amend this and say, first, we're going to do the grouping symbols. The grouping symbols include parentheses. It includes brackets. If only I could remember how to spell. Is it CK? Is it just K? Brackets. That doesn't look right. It's okay. Braces are another kind of grouping symbol. We'll talk about absolute value bars.
You had it right with the CK, sir.
It was CK.
Yeah.
Darn. Well, that's why I'm not an English teacher. Fraction bars are another kind of grouping symbol. So in terms of our priority or prioritizing which operations come first, we need to look at whatever is inside or sort of designated as part of some grouping symbol. Then we need to do everything that has an exponent. This is exponents or roots. Okay. And we haven't seen roots yet. You guys might know about square rooting things or cube rooting things, but we're going to talk about that at length a little bit later on. Then comes our multiplication and division. And it turns out that multiplication and division have the same priority. So we're going to do these from left to right. So when we work a problem, we're going to start with the grouping symbol stuff, simplify that. We're going to simplify whatever exponents we see. Once all the exponents are gone, we're going to check to see if we have multiplication and division. If the multiplication starts off first on the left-hand side of the problem, then we'll take care of the multiplication. But if the division comes first on the left-hand side of the problem, then we're just going to do the division first. So another reason why PEMDAS is a little bit oversimplified, because sometimes division is going to come before multiplication. And that's going to have to be okay. We're just going to do that left to right. The same thing is going to happen with addition and subtraction. It is not always the case that addition will come first, but because it has the same priority as subtraction. So we're going to do whatever, if we have addition and subtraction left over, we're going to do that from left to right. Okay, and by ensuring that we, go through these steps, we should all be getting to the same simplified result, provided that we haven't made any mistakes, any sort of mental errors where you added things wrong or you multiplied things wrong. Okay, a lot of times students will make the mistake of raising something to a power incorrectly. Like they'll say 2 to the third power is 2 times 3, but it's actually 2 times 2 times 2. Okay, so just got to be careful with that. When we see problems that have a lot more operations, you need to breathe and then take your time. Do not be on autopilot. Do not try to rush through it, especially if you know that you're prone to mistakes, because you're just going to beat yourself up for all the mistakes that you're going to end up making for rushing through these problems. And you don't need to do that.
Let me get that last one.
Addition and subtraction.
Okay, cool. Thank you.
Yeah, you got it. Okay, so let's look at this problem. 7 over 4. Sorry, this is times. I'm just gonna make a really big dot. 1/3 plus 4/5 times 1/2. Okay. So what I suggest is if you're getting used to the order of operations, what you should do is sort of write to yourself a little note of the step-by-step process that we're going to go through to resolve or simplify the expression. Seems that we have multiplication and addition here, and we have fractions. So we have to do a lot of mental juggling here. What is the first priority operation that we should take care of?
Multiplication.
Multiplication. And we have two multiplication symbols here. So we're gonna take a look at the first one, the one that's on the left, and just run through that multiplication. But we could take care of that simultaneous to doing the other multiplication, and it won't change the problem. So however you want to do that, what should I get when I multiply these two fractions together? Well, what is 7 times 1?
7/12 it should be.
Yeah, 7/12. Is everybody okay with that? Or does anybody have any questions about that? Maybe anybody confused? Again, I like to say that multiplying fractions is very straightforward. It is literally straightforward. You're going to multiply this number straightforward with that one, and this number straightforward with that one. Okay. We'll do the same process here for this second set of fractions that we're multiplying. So 4 times 1 is 4.
4/10.
Yeah, we should have 4/10 here. And then we're just going to drop our addition symbol down here. We're going to bring everything down. Okay. So now we have two fractions that we need to add. So we're back in the world of adding fractions. But we need to get a common denominator. So can anybody tell me what the least common denominator of 12 and 10 should be?
2.
2.
Ooh.
Okay.
So this is where I know in your head, those of you that are saying 2 are making the confusion with another concept that we call greatest common factor. You're thinking that 2 is a common factor of 12 and 10, right? And because 2 divides into both of them. But I'm asking for the least common denominator. Again, sort of a misnomer, sort of confusing. We need to think about the least common multiple. So what are the multiples of 12 and what are the multiples of 10? And then among those multiples, what is the one that's in common? So let's count by 12s. We have 12, 24, 36, 48, and then 60. And then I can do 10, 20, 30, 40, 50, 60. So in this list of multiples, the least common multiple, or the first number that they have in common, is what?
60.
60. So the least common denominator is sometimes a larger number than the ones that appear here. It's not going to be the smaller number that goes inside of both of them. Does that make sense? Or do we have any questions about that?
I've got a question.
Yeah.
Do you only simplify the final product, or could we simplify that 4/10 or no?
Yeah,
make
you
it
could
simpler?
you could simplify the 4/10 for sure.
That
I-
wouldn't change the answer?
Nope. You can simplify the fractions at any point in the problem, and you should, if you don't make any other mistakes, you should get to the same place.
Oh, okay.
Yeah, because remember, simplifying a fraction or writing an equivalent fraction doesn't change the value of that number. It just changes what it looks like. So it's not going to change the value of the problem. But in this case, I didn't want to get us bogged down with simplifying in the middle of the problem. I just wanted to say, let's simplify at the end of the problem.
Oh, okay, I get it.
So I said, let's look at 12, let's look at 10, and we look at the multiples of each. It looks like the least common multiple is 60. So I need to have a fraction that has a denominator of 60 for each of these fractions. Well, for this first fraction, what number did I have to multiply the 12 by to make it turn into a 60?
5.
5. So what I can do is go over here and say, I'm going to multiply this by 5/5. So the 5 times the 12 gives me the 60. That means 5 times the 7 should give me a what?
35.
35. So 35 over 60 is equivalent to 7 over 12. Now we're going to do that same process over here, but we need to ask ourselves 10 times what gives me this 60?
6.
6. So that means I need to multiply this fraction by 6 over 6. So I get the 60 on the bottom there, and then 4 times 6 should be 24. Does anybody have any questions up to that point? Well, now that I have these pizzas that have the same slices, the same size slices, I can just go ahead and add the numerators together and keep the slice size the same. The denominator is going to remain 60 for now. And 35 plus 24 should be 59.
Yeah.
Okay. Yeah. So you might say to yourself, well, I think that 59 seems to be a prime number. You know, for larger primes past 30, I'm not super familiar with the primes, although they do tend to be odd numbers. So that's one sort of mild implication that this might be a prime. But 60 can be broken down because that is composite. So if you want to explore whether this fraction reduces or not, we could do some scratch work over here. And I'm going to look at 59 and I'm going to look at 60. Because 60 is easier to do a prime factorization tree, I'm going to start with 60. So I might do 2 and 30. 2 is prime. 2 and 15. Again, 2 is prime. And then 3 and 5, and both of these are prime. So I could rewrite this fraction if I wanted to as something over 2 times 2 times 3 times 5. And so if this is going to reduce, then this 59 would have to be divisible by either 2, 3, or 5. So that's all I have to check in my calculator to see if I can reduce this fraction. So I could just go to my calculator now and say, okay, let's see if 59 is divisible by 2. It's not. We don't get a whole number. Let's see if it's divisible by 3. 59 divided by 3. Not divisible there. And it's not divisible by 5 because the multiples of 5 end in 5 or 0. So this has to be a fully simplified fraction. 59 must be prime. So we're done here. This is the result of simplifying our original algebraic expression. Does anybody have any questions, comments, or concerns about that problem?
So because you couldn't simplify the top, I mean, you're gonna just leave the bottom the way it is then, right, is what you're saying?
Yeah, I'm just going to leave the fraction alone because there's no common factors to cancel out and simplify. So if you can't simplify the fraction, you can't cancel out common factors, that's when you know you're done.
Gotcha.
Yeah. Okay, let's take a look at another problem. Maybe one that doesn't have fractions. Maybe one that does. Let's see. Yeah, let's do 1/6 to the third divided by 8 minus. Let's do 1/5. Let's mix it up, get some whole numbers and some fractions in there. Okay. Let's take a moment to write that down. Can anybody tell me what is the first operation that we need to take care of here? Maybe I'll write a little game plan to the side.
1/6 to the third.
Yeah, I mean, it looks like we have some parentheses here, but again, the parentheses here are just to indicate that we're raising the entire fraction to this exponent. So really, we're going to start off with exponents. Then we have division and subtraction next. So division takes priority over subtraction. And then we can do our subtraction and that'll be it. So there's our game plan. Remember, this is 1/6 times 3 copies of itself, right? or maybe times 2 additional copies of itself. So that's 1/6 times 1/6 times 1/6. We'll take care of that first, right? So this is the first thing we're going to do. And we get this jazz. 6 times 6 is going to be 36 times another 6. Oh man,
216,
it's what?
216?
Is it
No, wait.
260?
Yes, it is 6 times 6 times 6 is 216.
That escalated quickly. Yeah, so we should be able to take this to 1 over 200 and we said 216, right?
Yes, sir.
Sounds good. Well,
And then can we turn that 8 into a fraction, I suppose? Like 8 over 1, just to kind of keep all the sequences the same?
yeah, exactly. That's exactly right. So if we're dealing with a fraction and a whole number, we're going to want to change that whole number into a fraction. And then how do I divide fractions? What is the phrase that we learned last time?
I forgot.
Ooh,
Keep
It's
the
that
first.
first step, right?
The keep, change, flip.
yeah, yeah. Keep, change, flip, or keep, switch, flip, however you want to say it. We'll go ahead and change this expression, or this part of the expression. We'll keep this as 1 over 216. We'll multiply this by, this is 8 over 1. So we'll flip it to the reciprocal. That's 1 over 8 now. And then we'll go ahead and simplify that. And we can see that clearly I contrived this problem very poorly because it's escalating very quickly. The denominator is blowing up to a very large number. But that's okay. If you're doing all the steps right from what we've learned, you just have to roll with it. So 216 times 8, if we throw that in the calculator, we have 1728. Again, very strange looking fraction, I know, because the denominator is huge, but we just have to deal with it. We just got to live with it. As long as we can trust ourselves that we're doing the correct steps, don't second guess yourself. The processes that I've taught, as long as you're carrying them out faithfully, doesn't matter what the numbers look like. Believe in the process. Okay, so now we just need to subtract that 1/5. And I guarantee you that we don't want to list multiples of these guys. What we want to do instead is what we saw last time, where I took the 5 from this fraction and multiplied this by 5 over 5, just so that we don't have to think about it. And then we're going to multiply this fraction by, I know it seems weird, but we're just going to do it. 1728 over 1728.
Wait, what?
Remember from last time, we took the 5 and we multiplied 5 over 5 on this fraction. And then we take the denominator over here and multiply it by this fraction.
Oh, like a cross multiply?
Yeah, but we don't like to use that phrase.
We don't. Okay.
Me and the voices in my head, we don't. Because students tend to confuse cross multiplication with a lot of different concepts in math.
Yeah, I do that.
This is really what's called multiplying by a convenient form of 1. And it doesn't seem that convenient, but just remember that 5 over 5 is 1. So it's not going to change the value of this fraction. 1728 over 1728 is also just 1. So it's not going to change the value of this fraction. What it does do is change the denominators of the fraction so that they look the same. 5 times 1728 is going to be the same thing as 5 times 1728. So we'll have the same denominator.
So this is only because the numerator's 1, right?
What do you mean? No, you could do this
Like,
regardless of what the numerator is. Just like swap the denominator.
Get the same denominator?
That what?
Is it to get the same denominator?
Yeah, that's all we're concerned about. The numerator is going to change, but the important thing here is that we're going to get the same denominator. And the denominator is 8640. So 5 times this is 8640. 5 times that same thing is 8640. We have the same denominator now. It just so happens that for this one, 5 times 1 is 5. And 1 times 1728 is 1728. Looks really strange, right? These are super ugly fractions. But the process is consistent. You got to trust the process, even though these fractions look different or they look strange. So we're going to do this subtraction. And we might want to throw this in our calculator, 5 minus 1728. And you get negative 1723 over 8640. And this to me, because it's odd, looks like it's a prime number, or I'm not thinking that it's going to have any common factors with this number. So for now, because I sort of created a really monstrosity of a problem here, we're going to say that that's fully simplified. And we're going to move on to another problem. But the process, okay, so let's not get lost, lose the forest for the trees. We're talking right now about the order of operations. So we do have to process fractions in a lot of different ways, and you have to remember the rules for processing fractions, but we're talking about carrying out this game plan. Do the grouping symbols, the exponents, multiplication, division, addition, subtraction. And as long as you run through that process correctly, trust the process, and we should get our correct answer. Let's do a couple more that are a lot simpler than this, okay?
Trust the process.
Trust the process. It's all about process. Math is about process, not the numbers. At some point in very higher level mathematics that you probably will never be exposed to in your life, there aren't even any numbers. Okay, so let's look at some more practice problems. 6 to the third divided by 8 minus 5. That was the original problem before I decided to jack it up. So let's look at another one too. 8 squared plus 10 squared divided by 2 squared. And then, yeah, we'll just work on those two. So I'll give you guys about 3 to 5 minutes to work these out, and then we'll come back together and see what we get. And when you get the answers for these, you can go ahead and post them in the chat. You can separate them by a comma. That'll be fine. You can just type the answer to one and then comma the answer to the second one. Well, it looks like we're being really consistent across that first problem. Looks like everybody's coming out to 22. It looks like we have a sort of a tie as far as what we think the second problem simplifies to. So let's jump in and look at them. For the first practice problem, we need to do, if we're writing out our game plan, we need to take care of our exponents. Then we need to take care of the division and then the subtraction. So in my head, we sort of found in the last problem that 6 times 6 times 6 should be 216. When you divide that by 8, that should turn into 27. And then when you subtract the 5, you should get the final answer of 22. And it looks like most of us were getting that. Does anybody have any problems with that first practice problem? Any questions or concerns about it? Cool. All right. For this one, I would say we need to take care of all of our exponents first. Then we need to do our division. Then we need to do the addition. That is what the order of operations, or GEMDAS, prescribes to us. Okay, so right off the bat, we can take a look at 8 to the second power. That is 8 times 8. We can look at 10 to the second power, which is 10 times 10, and 2 to the second power, which is 2 times 2. So we should get 64, we should get 100, and we should get 4 here. I'm just going to bring down the remaining operations. Well, now, if we have our game plan set out right even before we start working with the numbers, division has a higher priority than addition. So we have to go ahead and do that division. So 100 divided by 4 is 25. And then that's what should give us our final answer of 89. Does anybody have any questions about that one? If you got 41, it is because you were on autopilot and not thinking about GEMDAS, or the order of operations, and you just did the exponents and then you ran from left to right. You did the addition first. So if in that case, you did 64 plus 100, which is 164, divided by 4, which gave you the 41. But you're not supposed to do addition first. You're supposed to do the division first. Does that make sense?
Got it.
Yeah, so be very careful. Again, when we're working through these like very simple math expressions and trying to simplify them, we have a tendency to go on autopilot and just start doing everything from left to right. But we need to slow down, unlearn that habit. And the habit that you should get into is at every step of the problem, we simplified the exponents. And then I should ask myself, what has the next priority, the next highest priority? Is it addition? Is it division? Like really slowing down and thinking about it, being very mindful as you move through this progression. Okay, so division is a more complicated operation than addition, so we have to do that one first. And then we can go ahead and take care of the addition last. If you do not slow down and think about it as you're working, you're going to have a really awful time. It's going to be so frustrating. And I just want you to avoid that frustration. Okay, so the thing that we're going to get into next time, because we don't have a whole lot of time left, is simplifying algebraic expressions. Right now, we have purely looked at numerical expressions. Notice that in those last problems that we worked, they were just numbers. There were no variables, even though at the very beginning of class, I talked about variables in our expressions. But pretty soon, we're going to be working with algebraic expressions. And you might have an algebraic expression like, let's say I went to the store and they are going to charge me for the 3 apples that I picked up, for the 2 bananas that I want to take. And then again, they have this really crappy credit card fee that's a flat $5 fee. And in this dystopian universe where you're getting charged $5 every time you use your credit card, every store does the same $5 flat fee. Maybe the tyrannical government has decreed that, you know, every time you use your credit card, you're going to get charged an extra $5. I don't know what that, you know, what is going on in this universe. But anyway, we're going to learn about these terms, right? We learned to count these terms before. This has 3 terms in this algebraic expression. There are 3 terms here. There's 2 different kinds of variables. There's 1 constant term. And because these variables are not the same kind, or these terms are not the same kind, I can't combine them. I can't say that I have 3 apples and 2 bananas, and that gives me 5 bananas. It wouldn't make sense to say, let's go ahead and add these 2 things together and then call it 5b, because then what happened to the apples? How did they magically transform into bananas? Okay, so we have to sort of keep our apples, our oranges, our bananas separate from each other. And if we cannot combine these terms because they're not the same kind of grocery item, then we just have to leave it alone. Okay. But then if I said at the store, we're given the prices of these items such that A is equal to $1 and B is equal to $2, then we can evaluate the algebraic expression.
What happens on certain math problems, they don't give us a key like that. You know, where I've seen the math problem as you wrote it, but there is no legend where it tells you A equals and B equals.
That's perfectly fine. It really depends on what the instructions are saying. So the instructions will be clear as to what they need you to do. And so if they say evaluate, then they will give you the values for the variables.
Okay.
If they say simplify the expression, and we'll talk about this next time, then we're going to do a process called combining like terms. So if you have like terms, you can combine them somehow.
Then you could end up with an answer with like something AB.
Yeah, something that has variables in it still.
And it will be like AB, the number plus, you know, whatever AB on the side of it. No?
Yeah.
Okay.
Yeah, but we'll get to it next time. So if I were evaluating this expression, and we're going to do a whole lot of this next time, what we're going to do is substitute the variable value into the expression and then simplify. So we would rewrite our expression as 3, and what I like to do is open up a set of parentheses, right? Because our variable is just a placeholder. It's a placeholder for the value we're going to put here. So if this is 3a and a is 1, well, then I'm just going to write 3 times 1 plus 2 times b, which is worth 2, plus 5. Now I have a purely numeric expression, and I can use my order of operations to simplify it. I have multiplication here, and then I have addition. So in this case, if we're using our order of operations, we'll want to take care of the multiplication. That will give us 3 here. 3 times 1 is 3. We can take care of this multiplication. 2 times 2 is 4. And then we'll bring everything else down. So we have plus, plus, and then we have a 5. And now we're just adding up numbers. The addition, because we only have addition, it doesn't matter. They have the same priority. We're just going to add them straight across. This is going to be 7 plus 5, which is 12. And we have evaluated our algebraic expression given the variable values. Okay. So we're going to get into more of that later. I just wanted to sort of preview it. How the algebraic expressions and order of operations are going to be intertwined. Okay, but that's all the time we have for today. So I'm going to go ahead and stop sharing my screen. you guys are free to go. If you do have questions, you can hang back and you can ask me those questions. Otherwise, it's Thursday. I will see you guys next week.
Have a great weekend.
You too.
Thank you.